Greetings everyone. Today we will be discussing about some aspects of work and energy of our BSc Mechanics course. So let us go to the slides. We see that from Newton's law of motion, we get mdv by dt is equal to f of r, where f is a function of distance. Now integrating the equation in one dimension, that is we will be taking the x part, like m d square x, it is ma, so d square x by dt square is equal to f of x, where m d square x by dt square is also m dv by dt is equal to f. Let us name this as equation 1. Now integrating left hand side and right hand side, you get m. It will go from one point to another, no? So you will xa to xb dv by dt dx, xa to xb fx dx. Now here we know dx is equal to dx by dt dt, which can be written again as dx by dt is v dt. So now changing variable from x to t, since the variation has changed from x to t, we will write m xa xb dv by dt dx can be written as m ta tb dv by dt v dt. You must notice here variation is with respect to t, we cannot expect a variable again integration with respect to x. So we have used this relation such that our variation is with respect to t only. Now let us look at equation 3 very carefully when we know what is how to integrate it. So first dv by dt v can be written as dv d by dt of half v square. M we can take outside safely, and this comes out to be what? Again half m, and what will be this d by dt of v square, integration is v square tb by t, which comes out to be, we know v at time tb will be vb, v at time ta will be va. So our expression becomes, our left hand side expression becomes what? Half m vb square minus half m va square, that is half m vb square is the vb is the final velocity, va is the initial velocity. Now what was the right hand side? Right hand side was xa to xb fx dx. This expression here, let us try to remember our title. Our title was work and energy. See, this is an expression for kinetic energy, and f dx is an expression for work. So we have derived the general expression for work and energy, and we will be using it in our specific problems. The first problem is a very common problem. A mass thrown upward in a uniform gravitational field. We know when the mass is thrown, when a mass is thrown, let us say a ball is thrown upwards in z-axis, let us say, the force of gravity acts downwards. So your force will be f is equal to minus mg. Now we will substitute. See, the mass, you are throwing a ball upwards. So on substituting the work energy expressions, that is half m f square, I have written f is the final velocity, I is the initial velocity. So half m f vf square minus half m vi square, that is our equation number 5, is equal to zi to zf f dx. We have deliberately used z because, as we have said, we have thrown the ball in the z direction. Now once you do that, what do we get? We get is, you know, when you throw a ball, the point here will be maximum velocity, at the topmost v will be 0. So here vi is equal to v0, initial velocity, vf is equal to 0. So what happens again? What is f? F is minus mg. So substitute here. This part becomes 0. It becomes half mv0 square is equal to f. What is it? F dz, which is zi to zf. So this will become zi zf minus mg. Now we can write here also minus, because this is also minus. So minus will cancel. v0 by 2 is equal to dz, because you can easily take m and write g here. So this is v0 by 2 g zf by zi, zf by zi dz. So v square by 2 on integration gives g zf minus zi, or zf final displacement is equal to zi plus v0 square by 2g. This is very similar to the expressions we have derived in our lower classes. So that is not new. Only thing is we have not specified the direction so accurately. We can write any S. We can write some S like that in lower classes. But here, since we are pointing it in the upward direction, we are writing Z. So this is a very common expression when we learn about gravity. So ZF is, that is final displacement is equal to Zi initial plus V0 squares by 2G. This is an important finding. Now let us take another example. Here, what we have done is solving the equation of a simple harmonic motion using simple harmonic motion. So we know what is simple harmonic motion. That is a mass connected to a spring. It will have to and forth motion. That is why it can stretch up to here. It can come back also. Or a pendulum, to and fro motion. It was in the mean position, then it goes here, then it can go like here, and then again come back to the mean position. So the restoring force in simple harmonic motion is F is equal to minus kx. When we talk about a spring, so that is, consider a mass attached to a spring of force constant k executing simple harmonic motion, where F is equal to minus kx. Substituting equation 5, here what it will be? Half mv square minus half mv0 square is equal to minus k x0 to x dx. Okay. Now here, this comes out to be actually, it is equation 6. So minus kx actually is f dx. That you must remember from our equation 5. This is our equation 5. This is fx dx. So here it is, fx is minus kx. So kx x0 to x. We are writing x direction, x0 to x dx. And then what will be the integration? We have got the integration here. Now, let us consider a case where at t is equal to 0, the mass is released from rest. So V0 is equal to 0 at a distance x0 from origin. So that is very much clear. That is, when you are releasing the spring, when you are stretching the spring, initially at t is equal to 0, V0 is equal to 0. So the first term, so the second term, that half mv square minus half mv0 square, that term goes to 0. So our left hand side is only left with half mv square. Right hand side is the same. Minus kx square plus kx naught square. So we will solve for v square. V square will come out to be minus k by m x square plus k by m x naught square. We know dx by dt is equal to v. So v will be root of this expression. Root of k by m, k0 square minus x square. Now, let us look at equation number 7. Using equation number and separating the variables. Here it was dx by dt. See, here it was dx by dt is equal to root k by m x naught square minus x square. So bring x naught square here, dt there. In all our knowledge of our angular momentum and other things, we have realized root k by m, generally we write it as omega. So let us write this as omega dt. And on solving x0 to x, this we know is sine inverse x by x0. This integral is a standard integral, and this we will get it as what? Yes, initial condition, initial is 0, final is t. So omega dt 0 to t. So we will write omega t. So it is x0 from x, sine inverse x0 from x. Substitute for x, x0 is fixed, you must know. So substituting for x, the first term comes to be sine inverse x by x0. Okay, the second term comes as minus sine inverse x0 by x0, which is sine inverse 1 is equal to omega t. We know what is sine inverse 1. Sine inverse 1 is pi by 2. So, finally our x by x0 is, when you do that, it is sine omega t plus pi by 2, which is cos omega t. So, our solution is x is equal to x0 cos omega t, which is the standard solution for a simple harmonic motion. So, this solution satisfies the initial conditions at t is equal to 0, x is equal to 0, and the initial velocity vi is equal to 0. So therefore, the work energy theorem in one dimension, this is half mf square minus half vi square is equal to f dx, where xi2, where the integration is from xi to x, such that in the beginning itself I have told it is kf minus ki, kinetic energy, is equal to wfi, which is the work. And this is precisely our work energy theorem, which we have derived and used in these examples in our presentation. So that's it. Thank you.